All right, so welcome back, everybody. We only have 2 days of lecture left. We have a day of lecture today, obviously, and then Tuesday of next week. But next week is kind of a half week because by the time Thursday rolls around, that's when we would normally have lecture. We're already in finals. So yeah, we just meet today and then on Tuesday, and then that's it. After that, it's just the final exam. And as I said before, we're not going to cover anything new during these last 2 days. Instead, we're just going to use those 2 days to review. All right, so a few things to note. We have final exam review problems, just like we do for every test, except we won't have time next week to go through them in lab. So instead, just go through these at home. Take a copy of the packet up here if you haven't done so already, and go through these problems that you studied. Next week, probably around Thursday or so, I'll post the solutions, just like I always do. All right? The other thing is test corrections. I handed back your tests, so if you came in late and you didn't get it yet, just grab it at the end of class. Test corrections will be due on Tuesday next week. That's our very last day of lecture. So if you want to do test corrections, you'll have to submit them by Tuesday next week. Okay? And then besides that, just a few things about the final. Again, the final is going to be on May 17th. That's a Tuesday. And it's going to be in this room from 5 to 7:30 p.m. So just note the different start time. Okay, the final exam time slots don't match up with our class meeting times. It's a longer time slot, obviously, but it starts earlier. Okay, so you got to get earlier, here earlier than usual to the final exam. So it's 5 to 7:30. As far as what's on it, it's cumulative. We've covered all the content we're going to cover in the class, so any of that stuff might potentially appear on the final. As far as the length, you should expect something that's longer, 8 to 10 problems, as opposed to our usual like 5 to 6. And that's because we need to cover more content and we have more time to take it. So per problem, it's about the same as what you're used to, but it's just longer overall. And because of that, your cheat sheet can be a full sheet of paper, front and back, because obviously you need more equations on there for the final. All right? So again, no lab next week. So go over these problems at home to study, and the solutions are going to be up on Canvas by next week. All right? So any questions on any of that stuff? Anything at all? All right. So let's launch into a course recap. So what we've covered in this class touches on content from chapters 1 through 6 of volume 1 of our textbook. That's OpenStax University Physics. But then we also did parts of 9 and 13. So that's what we're going to get into here. And we're going to start from the beginning. Remember the stuff we did in the very first week of class, dealing with like units and sig figs? You know, some people get dinged small amounts on the test because of issues like this, so it's worth just going over real quick again. Remember, sig figs, significant figures, are the digits in some kind of measurement that we actually know, given how precise the measurement was. So when you measure something, you can't just write down an infinite string of digits, let's say for measuring a length or a time interval, because whatever you're using to measure that quantity has a limited precision to it, right? It doesn't have infinite precision. That's why you can't have infinite sig figs. You have to cut it off somewhere. So for example, let's say we're using a ruler to make our measurement. Remember, a ruler has the smallest division at a millimeter, or 0.1 centimeters. So it makes sense to go to the nearest tenth of a centimeter, like 13.5. But if I were making a measurement of length with the ruler and I expressed it this way, 13.5339997 centimeters, obviously, these last digits here are meaningless because we couldn't possibly know those, right? So that's the whole point of sig figs. The other issue is, okay, how do we take some measurement given to some level of precision, given to some number of sig figs, and then do some kind of calculation with that number? Remember, there's just two rules here. One applies to addition, subtraction, and the other applies to multiplication or division. Okay, so when you're adding or subtracting numbers, you got to round the result to the smallest number of decimal places out of the numbers involved in that calculation. So this is the example, 1.32 plus 1.2. you just punch that into your calculator, gives 1.52. But I'm putting the little bar above the 5 because that's the smallest number of decimal places out of these two, right? We go to the tenths place if we compare the two numbers. So then I'd want to record that as actually 1.5. All right? And then when it comes to multiplying or dividing, it's a slightly different rule. The rule is we round the result to the smallest number of significant figures out of all the numbers in our calculation. So a quick example is 12 times 3.95. Let's say those are two measurements that are going into some calculation. If you punch that into your calculator, you'll get 47.4. But because the first number has 2 sig figs and the second number has 3, we run around to 2 sig figs. That's the smallest number of sig figs out of those two numbers. So we put it at 47. Okay? So we all remember this stuff? All right, let's move on. How about units? Okay, it's important to be able to do basic unit conversions. They come up a lot. For example, sometimes we'll have a quantity of speed, let's say, in miles per hour or kilometers per second, and maybe you want to get that into meters per second. So how do we do unit conversions in general? Well, you need a conversion factor, all right? Remember, conversion factors are just ratios of two quantities that are actually the same thing, just expressed in two different units. Like, for example, 12 inches over 1 feet, that's a conversion factor because it's the same exact quantity on the top and bottom. So it's really just 1, if you think about it, right? Like 3 over 3 equals 1, 5 over 5 equals 1. And of course, I can just multiply by 1 and not really change anything. That's the whole logic behind conversion factors. And no matter how many of these we put to multiply by, we're just multiplying by 1 repeatedly. So we're never really changing the quantity, we're just expressing it in a different unit, okay? So the idea behind all unit conversions is just to find the correct set of conversion factors that gets you to the final quantity you need. And if you just write them all out and see that things cancel in the right way, it's pretty straightforward. So let's do this one right here. How many seconds in 1 day? So this can be thought of as a unit conversion where our original quantity is 1 day, and we're trying to get it into this final unit of seconds, okay? So, okay, 1 day, that's what we start with. Let's take it in as many steps as we can, right? What would be like the next conversion factor that logically comes after this? Hours. Yeah, maybe go to hours. And, okay, so how many hours a day? 24. But how do I want to express it? Do I want to have that 24 over 1 or 1 over 24? Which one is it? Yeah, so I know that because if I write it as 24 hours divided by 1 day, then days cancel. Okay, that's how I know which way to express the ratio. Okay, so we'll cancel days. Now we have hours. Okay, what's the next conversion factor? 60 minutes in 1 hour. Yeah, 60 minutes divided by 1 hour, and then we cancel hours. And then lastly, 60 seconds divided by 1 minute, and then we cancel minutes. Okay, so every unit conversion, I mean, this is not the most complicated one in the world, but they all work in this way, okay? Just find the appropriate set of factors, cancel out the units until you get the unit you want, okay? So if you crunch those numbers, you know, it's 24 times 60 times 60, 86,400 seconds in a day, okay? So Sig Figs, units, let's move on to the next thing. Kinematics. Kinematics was the next topic that we covered in this class. So I just want to remind you about this stuff because it's been a while, right? Kinematics, what this means when we talk about kinematics is just a description of some kind of motion that's happening, but we're not really interested in the causes of motion, okay? So just describing motion in terms of things like position, velocity, acceleration. If we're just sticking to those types of quantities, we're in the realm of kinematics. And so we start with position. That's the most kind of basic kinematic quantity we can think of. It's just a set of coordinates that tells you where something is located. And of course, if we're talking about a set of coordinates, we need some kind of coordinate system that we're working in, so we're clear on what we mean. So in one dimension, let's say, we started with one-dimensional motion, where things just move along a straight line. We usually use the x-axis to locate where things are. Okay, so here's my x-axis, here's the origin, and this position would be x equals -1 meter, right? So that's all you need in one dimension, just single coordinate. In 2 dimensions, you need x, y. In 3 dimensions, you need x, y, z. All right, velocity. Velocity tells you how quickly an object's position is changing. So remember, we kind of think of it sort of 2 ways. We have like an average velocity, and then we have what's called an instantaneous velocity. Average velocity is defined like this. It's delta x divided by delta t. So it's delta x is, what's another name for delta x? Do you guys remember?
Change in x.
Yeah, it's a change in x, but it has the name displacement. Yeah, that's right. So displacement divided by how much time it takes to actually do that displacement, that's your average velocity. And of course, like delta t can be some time interval. Might be a minute long, might be 10 minutes long, might be a second long, but it's not just one moment in time, right? If we take the limit where delta t goes to 0, then we have what's called the instantaneous velocity, which is like a derivative, dx dt, okay? And then we can play that same game one more time, basically to get acceleration. Okay, so acceleration tells you how quickly something's velocity is changing. So A is delta v divided by delta t. That's the definition of it. So change in velocity divided by some kind of time interval. And again, if we take that time interval to go to 0, then we have what's called the instantaneous velocity, which is instantaneous acceleration, which is a derivative of velocity with respect to time, right? So those are just the definitions. Just remember what these things mean. And actually, that brings us to the first problem I wanted to go over. So I'm going to go through the review slides kind of quick. I want to maybe spend more time on the problems, if that's all right with you. I think that's the best way to spend the time. Here's the problem. We have a velocity versus time graph for a track and field athlete. So we have velocity on this axis, time on this axis. We have a whole bunch of questions about this motion. Let's start up here. Let's answer these 2 questions. When is the athlete at rest, and when is the athlete accelerating? Can anyone tell me, just looking at this graph, when is the athlete at rest?
10 to 5.
Sorry, what was it?
From 10 to 15.
Oh yeah, 10 to 15. Right, good. Right, because what does it mean to be at rest? It means you have 0 velocity. So you have 0 velocity between 10 and 15 seconds. What would we say about acceleration?
0, 5, 25 to 30.
All right, well, let's take that 0 to 5. Velocity is actually remaining constant at a value of 10 meters per second from 0 to 5. So we wouldn't say it's accelerating there.
Okay.
So it's accelerating when the velocity is changing, right? So when do you see a velocity that's changing? Yeah, I would, well, it's, yeah, 5 to 10, correct. And then what else? 15 to 25, all right? So we agree it's at rest from 10 to 15 seconds, and then it's accelerating in 2 different time intervals. One of them is 5 to 10, and the other is 15 to 25, because obviously the velocity is changing during those times, okay? So, okay, let's calculate a few things here. What is the acceleration of the athlete at t equals 7.5 seconds? And then also, what is the acceleration at t equals 20 seconds? Let's start with that, and then we'll get to this last question. So how should I go about looking at this graph and determining acceleration? Take the slope. Good. Because remember, acceleration A is just delta v over delta t. On this graph, velocity is on the vertical axis, time is on the horizontal. So that's like a rise over a run type thing. That's a slope. So at 7.5 seconds, which is like right over here, we can simply just find the slope of this line. Just pick any 2 points on the line, and it will work. So How about I pick like this point as my final point and this point as my initial point, okay? And then for the other interval of time, let's say, you know, because I'm trying to find it at 20 seconds, which is over here, I just need to know the slope of this line. Let's take this to be my initial time, that to be my final time. All right? So let's just do it on paper real quick. A is equal to delta V over delta T. So if we're doing this, we can think of it as V final minus V initial divided by T final minus T initial, okay? So at T equals 7.5 seconds, we're looking at that first line segment that slopes down. The V final was 0 because we went all the way to 0 velocity at the end of that time interval. And do you remember where we started at? 10. So that was my V initial, right? 0 minus 10 is my change in velocity. And well, my T final was 10 seconds, and my T initial was 5 seconds. So it looks like I have minus 10 divided by 5, so that's minus 2. And look, the units are meters per second squared, okay? So we can do the same exact thing for the other time in question. And I'll just go back to the slide just so we have the data. So for this segment of the motion, what's my final velocity? Where do I end up at as far as velocity goes? I end up at negative 7.5 meters per second, and I start at 0. And what's my time interval? It goes from 15 to 25 seconds. So that means up here, I've got minus 7.5 meters per second as V final, minus 0 as V initial, divided by 25 seconds minus 15 seconds. That's minus 0.75 meters per second squared. So it's still accelerating in the negative direction, but just at a slower rate compared to before. So this is at t equals 20 seconds, what the acceleration is, okay? So hopefully that's looking familiar, right? How about this one? Last question. How far does the athlete travel between 0 and 5 seconds? So from here to here. So first thing I want to just establish, if we're looking at this segment of the motion from 0 to 5, what type of motion is going on? Are we accelerating? Are we not moving at all? Moving at constant velocity? What's going on? Yeah, it looks like we have a nice constant velocity motion going between 0 and 5. What is that velocity? 10 meters per second. Okay, so you could use a kinematic equation or something in this situation. That would work, but I think what's a little easier is this. Just remember that velocity, by definition, is delta x over delta t. Where in this case, we know what the velocity is, we know what the time interval is. We're simply trying to find delta x. So that's v delta t. And again, the velocity read from the graph was 10 meters per second, and it stayed there. And then our delta t was 5 seconds. So how far did we travel?
50 meters.
50 meters. Okay, so that's an example of just looking at a graph and trying to determine some aspects of the motion from it. All right, we need to know how to do that sort of thing. So any questions, or we just keep going ahead? All right, so that's just what we found. I'll leave it there for a sec, and we can move on to the next thing. All right, the next thing is kinematic equations. So hopefully this is all looking familiar, these kinematic equations. So these are a set of equations, we have 3 of them that we derived in class, which basically tell you something about how an object moves under constant acceleration. All right, so if you're moving with a constant acceleration, these equations are valid. If your acceleration is changing, you can't really use these. And that's kind of a topic for Physics 45, okay? So let's just maybe go through the first equation, and hopefully you can tell me just in words, what does each variable mean? Like, what does V mean?
Final velocity.
Final velocity in particular, right? Whereas V naught would be the initial, A is our acceleration, and T is how much time has elapsed. This is an equation where if you want to calculate the final velocity, it's super straightforward. Just plug in your initial velocity and your acceleration and your time, and you've got your final velocity. What about this one? X, that would be final position, X naught initial, plus V naught times time, plus a half AT squared. So this is an equation that gives you the final position of some object, okay? And this last one does not involve time, and it basically, if you remember, came from taking these first two and then like subbing out time as a variable. So if you're ever in a situation where you know some of the other variables, but not necessarily the time involved, this last one is useful for that, okay? All right, so I think that's it, except for this last thing, which is, remember we also have free fall kinematic equations. They're really the same exact set of equations, because if you're in free fall, you have a constant acceleration. It's just that it's a downward acceleration. So typically what we do is we set y to be the direction of motion for something in free fall, and the acceleration becomes minus g for a downward acceleration, where g is of course 9.8 meters per second squared. Okay, let's do an example. So this is an example of what's called like a two-body pursuit problem, where you have two different objects in motion, and one of them is like trying to catch the other, right? So let's say you're standing at the bus stop, and your friend is running towards you at a constant speed of 5 meters per second. Your friend slaps you on the back of the head, and then continues running away from you at the same constant speed. Because you're in shock, you hesitate before you start chasing after your friend. So let's say your friend is 5 meters out ahead of you. That's when you start chasing after your friend. So what you do is you start to run with a constant acceleration of 2 meters per second squared. All right? So that's what's going on. Your friend is just moving at a constant speed, not changing velocity whatsoever, and you start from rest and you accelerate towards your friend, but you start behind. So the question is, how long will it take for you to catch up with your friend? Let's work that out, all right? So let's draw a picture. All these kinematics problems are much easier solved if you draw a picture. So let's say that the moment you start running, that'll be t equals 0. And what does the situation look like at t equals 0? Well, you're located over here, and your friend is over here, running away from you at 5 meters per second. And also your friend is located 5 meters ahead of you. So I'm going to draw an x-axis to keep track of where everybody is. And it doesn't matter where I put the origin. It doesn't matter where on this axis I label x equals 0, as long as I'm showing that these two are 5 meters apart. So let's put you at the origin and your friend at 5 meters. That'll work, right? Okay. So what I'm going to do next is just write down a general kinematic equation that is going to be useful here. It says x equals x naught plus v naught t plus a half at squared, okay? We can apply that equation both to your motion and your friend's motion. And so we can have, in other words, like x is a function of time for both you and your friend. But what does it mean to catch up? What does it mean when you're at the, when you've caught up to your friend? What can we say about the x values? Yeah. So when you catch your friend, xy equals xf. You have the same position, okay? So let's do this. Let's say xy. That's your position. Let's just put numbers in for all these different variables, except for time, which we'll leave alone. Okay, so what's x naught? What's your initial position according to our coordinates here?
Zero.
That's 0. What's your initial velocity?
0.
Also 0, because you start off at rest, okay? But you have an acceleration, which is 2 meters per second squared. So it's a half times 2 meters per second squared times t squared. That's how I apply this formula to your motion. For your friend's motion, what should I do? What's x naught for your friend's motion? Yeah, your friend starts off 5 meters ahead, so there it is. And then, of course, there's a starting velocity. It's 5 meters per second, right? So that's v naught right there. And that multiplies t, but your friend is not accelerating. So that last term is 0, okay? So basically, if I set these two formulas equal to one another, and then I can solve for the time, okay? And what am I going to have to do? Like, what math principle am I going to have to use to find t? It's a quadratic expression because I have a t squared, a t, and a constant term. So the quadratic formula is going to come in. All right, but here, let's do the, first things first, xy equals xf, meaning a half times 2 is just 1. Just write it as 1 meter per second squared, t squared equals 5 meters plus 5 meters per second times t. That's not in the standard form for a quadratic, right? What should I do? So make it something where I can apply the quadratic formula to it. Yeah, I just got to move all the terms to one side of the equation. So how about I'll just move these two terms over to the left by subtracting them. So I have 1 meter per second squared, t squared, and then minus, I'll say plus negative, 5 meters per second times t, so that's moving that over, and then plus negative 5 meters equals 0. Okay, so do you guys recognize what the a, b, and c terms are here? What's the a term? Okay, yeah, it's kind of already laid out as a, b, c, right? So we have a, b, and c. All right, so now if I'm trying to find the time, I have to apply the quadratic formula. Can you remember what it is?
Negative b.
Negative b plus or minus the square root. Yep, and then divided by 2a. All right, so look, we know the numbers that are going into that. They're labeled right here. So this can be just punched into the calculator. But what you'll get is the following. You'll get either like 5.9 seconds or negative 0.9 seconds. You can verify that by punching these numbers in. But which one of these should I pick? See, a quadratic is always going to give you two solutions. So only one of them is physically relevant. So which one is it? Yeah. In this case, it's obvious it's going to be the positive one because the motion hasn't even started at negative times. So that's how long it takes after you start chasing your friend. 5.9 seconds to catch up. All right? Any questions on that one? All right, let's keep going. 5.9 seconds, there it is. All right, vectors. This is an important topic. So a vector is a quantity that has a magnitude and a direction. Vectors come up all the time in physics. And what I want to just remind you of here is that when it comes to a vector, we've learned about two basic ways to express that vector. You can either do it in polar form or in Cartesian form. So when we're in polar form, that means we have a magnitude and a direction, okay? And usually that direction is given as some sort of angle. We call this a polar angle. So if we're in an x, y coordinate system like this, the standard way to measure the angle is off the x-axis and you go counterclockwise, okay? You can measure the angles different ways, like off this axis, but this is sort of the standard. All right, when we talk about the magnitude of a vector, that's the length of this arrow on our diagram. When we talk about the components, that's how this arrow projects onto each axis. So if I like draw a line perpendicular down to the x-axis, that gives me ax right here. And then if I do the same thing on the y-axis, that gives me ay right here. So if you ever forget how to like go between the two forms, just remember you have a nice right triangle here, okay? So for example, the magnitude of a, that's the long side of that right triangle, it's just ax squared plus ay squared under the radical. And then the angle, we can think about that in terms of the tangent function. Tangent of this angle is going to be opposite over adjacent, so that's ay over ax, okay? Now if we want to go the other way, let's say we know the magnitude and the direction, but instead we want, ax and ay, we want the components. We just remember to use our sines and cosines, okay? So the x component of this vector would be the magnitude cosine of theta, the y component would be the magnitude times sine of theta. Okay, so hopefully that's all a review. Let's get to an example. So let's say we have two vectors which we have in polar form. A has a magnitude of 5 and a polar angle of 125 degrees. B has a magnitude of 4 and a polar angle of 260 degrees. So we're going to do two things here. We're going to first draw a diagram that shows the addition of these two vectors. And then we're going to actually calculate what the sum, like a plus b, actually is. Okay? All right. For the diagram, we're going to use the tip to tail method. Remember how this works? Start by drawing vector A. So A has a polar angle of 125 degrees. That puts it pointing into the second quadrant like this. Okay, so 125 degrees off the x-axis shows you where vector A is going. Then what we have to do is connect vector B to that first vector, and that one is at 260 degrees. Which quadrant, by the way, is that second vector in, given that it has a 260 degree angle? Which one? Third quadrant, right? But pretty far into it. It's almost pointing straight down, right? Because 270 would be pointing straight down, so we're almost there, right? So that's A and B tip to tail. Now, the resultant vector, which is the sum of A and B, is going to have to go like this. It goes from the start of A all the way to the end of B. And we could have done this with any number of vectors, of course. You can just keep chaining things together tip to tail if you have more than two vectors, but that's what it looks like with two. Okay? So that's how you get the picture. Now let's do a calculation. You guys remember how this works? How should I calculate the sum? Yeah, just add up their components, right? It's super easy to add vectors as long as everything is broken up into components, right? So let's start by just writing A and B separately in component form. So the resultant vector, I'll call that R, is A plus B. We're trying to figure out what that is. So on the first line, I'll write vector A in component form. So that's magnitude, which is 5, times cosine of the angle, which is 125 degrees. That would be my x component, right? Whereas my y component would be 5 times sine of 125 degrees. So I hat, j hat unit vectors come along for the ride. And then on the next line, I'll write down vector b. That has a magnitude of 4, angle of 260. So if I take the cosine of the angle multiplied by 4, that's the x component. And then for the y component, I have 4, and then sine of 260 degrees. Okay, so I've shown you this many times before, but when you're adding a bunch of vectors up, it's useful to draw them or write them each down on a separate line so you can see how the components sort of line up with each other, right? So overall, this is our x component. Overall, this is our y component when it all gets added together. So I'll just tell you what it is. You can verify. but you get minus 3.56 I hat. And we'll want to keep 2 sig figs on that, and then you'll have plus 0.16 j hat for the other component, okay? Now, as far as this resultant vector goes, which quadrant are we in, just based on the signs we got? We're in the second quadrant, right? So I'll just write Q2. It's going to be useful for later. Okay, so the magnitude of this resultant vector is the square root of rx squared plus ry squared. So that's going to be the square root of minus 3.56 squared plus 0.16 squared. And that's actually going to give me basically the same as 3.56. So because this component is so big compared to the y component, it almost makes no difference in this calculation. You can see that. But if we want to keep our sig figs straight, we round it to 3.6. Okay, so 3.6. Okay, lastly, we want the angle for this resultant vector. So we say tangent theta equals ry over rx. That's how it works. And of course, if I want to just figure out what the angle is, I have to use what again? Inverse tangent. And then because I'm in the second quadrant, what should I do? Yeah, that's right. So here, I'm going to take 0.16 over minus 3.56, inverse tangent of all that, and then add 180. And you can see that this works out to 177 degrees, which kind of makes sense given the picture we drew. The resultant vector in our picture was almost going directly along the minus x-axis, which would be 180 degrees, but it's a little bit less than that. Okay? All right, so vector addition. Any questions on that? Hopefully it's all ringing a bell. Okay? So there we have our answer. Resultant vector, magnitude 3.6, angle about 177 degrees. So from here to here. Let's do some other stuff. Projectile motion. All right, so projectile motion is referring to the motion of any object that's launched into the air and only moving under the influence of gravity. Okay? So obviously one major assumption we make when it comes to projectile motion is no air resistance. We're just neglecting that. The standard way to set up the coordinates is like this. X going horizontal, Y going vertical with up being positive Y. And because we know that objects that are projectiles under free fall accelerate down at a rate of 9.8 meters per second squared, we can basically use our kinematic equations that we already know, but we can put them in vector form because we're dealing with two-dimensional motion, x, y, and we can set our acceleration to this, okay? The acceleration of a projectile is 0 I hat. That means there is no acceleration going horizontally. Gravity does not act horizontally, so that makes sense. And then minus g times j hat. So the y component of gravity is going down. All right, so this is what we call a vector kinematic equation for position. It's the same one that we've seen before, except all quantities like position, which we call r, and velocity and acceleration, they're all now vectors. Okay? And same with this equation for velocity. Same equation from before, but everything is now a vector, right? I just want to remind you that whenever we have this type of situation, that we're always free to sort of break it up into components. So I have like a separate x and y equation for position and also for velocity, okay? So yeah, probably doesn't make sense to read these out for you because you've seen these before, so let's go to the example, okay? So here's the example. At t equals 0, we throw a rock off the edge of a cliff. The cliff is 105 meters tall, And the rock has an initial speed of 15 meters per second, and it's initially thrown at an angle of 35 degrees above the horizontal. So we have a number of questions that we want to answer about this. First one is, at what time will the rock hit the ground? Second question is, how far will it travel horizontally before hitting the ground? So what's like the horizontal distance from here to here? And then lastly, what is the maximum height above the ground that the rock is going to reach during its trajectory? So this is just an example of using all of those different kinematic equations that we just talked about. And as always, we'll start with a picture, right? It's helpful to draw a picture. So here, I'm going to draw a coordinate system to start off. X, Y axes. And I'm just going to set things up so that the cliff is like up here. We chuck the rock with some initial velocity, which I'm going to call V naught. And that rock moves through the air something like this. And then it lands on the ground over here. Okay? So these 2 points, let's start with that. These 2 points are the initial and final positions for the rock. And we might know some of those things about the rock, like what its initial position and maybe some parts of what its final position are. Let's start with this. What is the initial position of the rock in this coordinate system? Like x, y coordinates. What would the x coordinate be?
0.
Yeah, it'd be 0 just because of the way I set up my coordinate system with the origin down here. And then 105 meters, right? Because it's 105 meters up from the origin. All right, my final position. Do I know what the x coordinate is in the final position? No, I don't know what it is. That's part of the problem, is to find that actually. But do I know the y coordinate? 0. Yeah. So in terms of the y motion, we go from 105 meters to 0. In terms of the x motion, we go from 0 to some unknown final location. Okay? Let's do one other thing here. See this velocity, I'll kind of copy this because it's getting too cluttered, but this velocity is a vector which can be broken into x and y components, right? This is v naught x, and this is v naught y, and this is our launch angle. Okay? So if I'm trying to find the time of landing, it's helpful to use this equation. I'll just write it down for you. Y equals y naught plus v naught y times time minus a half gt squared. And how should I think about v naught y given this picture we just drew?
V sine 35 degrees.
Yeah, it's just I'm gonna do it symbolically for now, but yeah, it's just your initial speed, which is v naught, times sine of your launch angle, okay? Whereas v naught x, that's gonna come into play later. That's your initial speed v naught times cosine of your launch angle, all right? So, that's useful. Let's put in all the numbers we know into this equation. So y, that's our final y position. What goes right there? 0, right? Because we end up on the ground. Y naught, that's our initial y position. What goes in for that? 105 meters. Okay, then we have plus v naught y. Okay, that's going to be the initial speed, which was 15 meters per second times, times sine of the angle, which was 35 degrees. And then that multiplies t. And then we have minus a half gt squared. We have minus a half times 9.8 meters per second squared times t squared. So the reason I wrote this down as an equation to use is when you put in all the numbers you know, you see that the only unknown is t. T represents the time of landing. How long does it take to go from here to here? Okay? And again, it looks like we have a quadratic. We've seen this before. So let me just ask you real quick, what's 15 times sine of 35? I want to put a number to that. 15 times sine of 35.
8.6.
Yeah, it's like 8.60. So in a more compact way, I can write this as 0 equals 105 plus 15 sine 35 works out to 8.60. I should say this is in meters per second, by the way, times t. And then plus half of 9.8 with a negative sign is minus 4.9. And that's in meters per second squared. Okay? So there's our quadratic right there, where we have a, that's going to be minus 4.9. That's going to be the term that multiplies t squared. This is our b term, and this is our c term. So we've done the quadratic formula before. Remember, it's minus b plus or minus square root b squared minus 4ac over 2a. So for this quadratic, we put the numbers in, and here are the two solutions we get. One of them is positive 5.589 seconds. The other is negative 3.834 seconds. So how long does it take to land? 5.59 seconds is the answer. We can ignore the negative time because it's not relevant. All right, so we have that time of landing. It's going to be useful later. The second question was how far does it travel from this initial launch point to the landing point in just the horizontal direction? Any ideas how I can get that? What kind of kinematic equation might be useful?
X0 plus B0 xt.
Yeah, so just like I use this kinematic equation for position in the y direction to do this work, we can also look at the x direction. So the x kinematic equation for a projectile says x equals x0 plus v0 x times time. And notice it doesn't have that acceleration term. It's important to remember that. There's no acceleration on the x-axis. So for this one, we can actually just plug in the numbers. What do we know x0 to be here? 0, right? That's where we start. And then plus v0 x. Well, that's going to be our initial speed times cosine of the launch angle. So rather than saying 15 sine 35, we're going to say 15 cosine 35. So 15 meters per second cosine 35 degrees. And then now t comes in, so we're plugging in this time because we want to know how far has it traveled in total by the time it's landed, right? So we're going to plug in 5.589 seconds. And someone out there, do the number crunching for me. Tell me what you get.
68.67.
Yeah, so I'm getting exactly the same thing, 68.7 meters. So that's how far horizontally the rock goes. Okay, the last one, last question is, what is the maximum height? So actually, let's draw that. The maximum height from the ground to the peak of the motion. Any ideas how we could get that? There's something special happens when a projectile reaches its maximum height. Do you remember? Okay, so you had it, velocity is 0, but more specifically, it's the y velocity goes to 0, right? The x velocity is not 0, it's still traveling to the right. But the y velocity momentarily goes to 0 at the peak of the motion, okay? So that's what we're going to use. At the highest point, Vy is equal to 0. That's the property we're going to use here. Okay, so Any ideas, like what kinematic equation we could, I mean, we could do this multiple different ways, but what's the most straightforward way to go? Which kinematic equation could I use here? Do we know the time that the projectile reaches the maximum height? We don't know that actually. We know the time it lands. We don't know the time it reaches its maximum height. So if time is unknown to us, maybe we want to use this equation, which says vy squared equals v naught y squared minus 2g y minus y naught. All right? So let's put in everything we know. Vy, that represents our final velocity. So if we're just considering, so let's be clear, when I apply this equation, I'm saying this is my initial state right here when it's thrown, and then this is my final state when it reaches the peak, okay? So I'm going from here to here. My final velocity is 0, given what we just said, and my initial is v naught sine of the angle. We already established that, so it's 15 meters per second times sine of 35 degrees. And we're squaring that whole thing right there. So that's v naught y. All right, then we have minus 2 times g, which is 9.8 meters per second squared. And then we have y, which we don't know. Y is the final height off the ground. So let's leave it as a variable. But we can subtract off y naught, which is the initial height off the ground, which is 105 meters. Okay? So does it make sense how I set this up, everybody? All right. I'm going to go ahead and skip some of the algebra, just so we can get to other stuff. I'm sure you know how to solve for y, right? If you do it, you're going to find y is 109 meters. Okay? So 109 meters is what you get from solving for y. So that means this peak height off the ground is 109 meters. All right? Any questions? All right, let's keep going. All right, so those are the answers. Takes 5.59 seconds to land, travel 68.7 meters this way, and you reach a height, a maximum height of 109 meters off the ground. All right, next thing. I don't know about you, but a lot of people who have taken 44 say that this is the trickiest topic. I'm not sure if you would agree. Yeah? Okay. So let's go over a relative velocity problem. And then before that, let's just talk about what this is all about. So if I'm going to say, some object has some velocity, the car going down the street has a velocity of 35 meters per second, let's say. It only makes sense to make a statement like that relative to some kind of frame of reference. Motion is relative in physics, meaning it only makes sense to refer to some velocity relative to some frame of reference. And when we say frame of reference, we just mean a coordinate system. Which coordinate system are you measuring that velocity with respect to? Okay? So this equation right here, again, on its face, doesn't look like much is going on, but it's tricky. Because what this equation does is it allows you to relate a velocity as seen in two different frames of reference. Okay? So remember, we have this sort of double subscript notation to get everything in this equation straight. Let's see what it says. This says VOA. That's the velocity measured with respect to frame A for some object. Okay, that's equal to VOB. That's the velocity of some object with respect to some other frame of reference, which we'll call B. And then plus VBA. That's the velocity of the frames with respect to one another. Okay? So to give you something a little bit more concrete here, right, because it's abstract, let's say you're on a moving train and you throw a ball, okay? You could talk about the velocity of the ball as people on the train would see it, or you could talk about the velocity of the ball as people standing on the ground, not moving with the train would see it. And those would be two different things, right? And this is how you can go between those two perspectives, all right? So I think the best way to go is just to get into the example, okay? Here's the example I wanted to discuss with you. So the wind is blowing at 50 miles per hour in a direction 30 degrees north of east. The pilot of a plane is flying with an airspeed of 400 miles per hour. Okay, so when we say airspeed here, we mean the speed of the plane relative to the air, relative to the wind, which is different than the plane relative to the ground, okay? So the first question is, what direction does the pilot need to point the aircraft in order just to travel north relative to the ground? So we're kind of flying into the wind a little bit, so the wind doesn't carry us in a direction we don't want to go. It's kind of one of those situations, okay? So we'll get that direction. Then we'll answer the second question, which is, what is the speed of the plane relative to the ground? How fast is it moving? So again, it's moving 400 miles per hour relative to the air. Doesn't mean it's moving that fast relative to the ground. Those are different things. So, okay, let's get into it. So first thing is, how do we set up our equation? Well, we're going to be using these like subscript labels for everything. So let's just put that on the page to make sure we all know what we're talking about. Let's use the subscript P for the plane. It's pretty obvious. W, that's going to be a frame of reference moving with the wind. Okay, and then G, that's going to be a different frame of reference that's fixed to the ground. Okay, so the relative velocity equation is going to just say the velocity of the plane measured in one frame of reference, let's say VPG, can be related to the other velocity like so. So the velocity of the plane relative to the ground equals the velocity of the plane relative to the wind plus the velocity of the wind relative to the ground. So I just need to write some equation on the page. How do I know it's the correct equation? Remember, there's a little trick. The subscripts can appear in a certain order. If P is the subscript on this side, on the left, it should be on the left on this side. So that matches, right? If G is the subscript on the right over here, it should be on the right on that side as well. And then the W subscript would be on the inside and not appear over here. Okay? So y'all remember that? What I want to do here is establish what do we know about each one of these vectors, okay? So in terms of the magnitude and the direction. So I have three different vectors. I'm going to write what do I know about the magnitude, what do I know about the direction, okay? For each one. Okay, the velocity of the plane relative to the ground. The magnitude of that would be the speed that we're moving relative to the ground. Do we know that? But be careful, we don't know that because 400 miles per hour is actually this one. It's the magnitude of VPW. It's how fast we're moving relative to the wind, okay? So that's the 400 miles per hour right here. All right, the magnitude of this one is just the speed of the wind, how fast that's moving relative to the ground. That was 50 miles per hour. And we also are given a direction for this one, so let me just write it down. The wind is blowing at 30 degrees north of east. Okay, let's keep moving on this. For the velocity of the plane relative to the wind, we don't know the direction of that one. That's something we're going to try to find. That's basically how we have to point the aircraft, what direction we have to point the aircraft in. But for this one, VPG, velocity of the plane relative to the ground, we do know the direction. We want that to be due north, okay? So, I mean, think of this in a practical sense, right? Like if I have a city down here that I start out, let's say, I don't know, Santa Ana, and I want to end up somewhere that's pretty much straight shot north from there, right? Can't think of a good example. Somewhere in Washington, right? And let's say the wind is blowing in this direction, 30 degrees north of east. You see, I'd have to point the airplane into the wind a little bit so that I don't get carried down with the wind, so I can just travel straight north. But the point is, relative to the ground, I know that this direction is just due north, okay? So that's everything we know right there. Does that make sense? So I'm going to put a visual aid on the picture too. We're going to show this equation using a vector diagram, tip to tail, all right? So just remember how this works. Velocity of the plane relative to the wind plus the velocity of the wind relative to the ground. Those are the two vectors being added. So if I just draw each one of them and connect them tip to tail, then I get this vector as a result. So I can draw that all out, right? So here, let's put our coordinates on the page. We have east corresponding to x, that's the typical thing, and then north corresponding to y. So the velocity of the plane relative to the wind. I'm going to claim that this has to be in the second quadrant somewhat like this. So that when we add it to this vector, which is the wind relative to the ground, that's in the first quadrant, something like this. That can give us a resultant vector that's pointing due north, which is exactly what we want to happen, okay? So we agree that's what the vector addition should look like? Yeah, kind of? All right, so I'm going to label a few things on here. For the wind relative to the ground, this angle it makes off the x-axis is 30 degrees. And for the plane relative to the wind, we don't know what angle it's at. I'll say the angle off the x-axis is theta, and we're going to determine what theta is. We'll do that first, okay? So I think the best way to handle this problem is to take our original equation and just break it into an x component and a y component, okay? So here, let's start with an x equation. So for my x equation, I have velocity of the plane relative to the ground, but just picking out the x component of that equals the velocity of the plane relative to the wind, again, just the x component, plus the velocity of the wind relative to the ground, just the x component. Okay. So we're going to go term by term and figure out what we can plug in. For this one, velocity of the plane relative to the ground, x component, what is that? X being east-west motion. It's 0, right? Because there is no east-west motion. We're just going straight north. So this x component is 0. Okay? Now, for the plane relative to the wind, the x component. Well, how do we think about the x component of any vector? It's like the magnitude of it times cosine of some angle, theta, right there. So the magnitude, remember we have this information up here, is 400 miles per hour. And then we have cosine of theta, which we're going to determine. We'll figure out what theta is. For the wind relative to the ground, that velocity, we know both the magnitude and the direction. So it's pretty simple to write the x component, right? That's going to be 50 miles per hour cosine of 30 degrees. Do we agree? Does that make sense? And look, the only unknown is theta, which basically is telling us which way is the pilot going to have to aim the aircraft. Okay? So let's just do the calculation real quick. We have cosine theta. If we solve for that, if we isolate that, I have to subtract this piece. So I have minus 50 miles per hour cosine 30. And then I have to divide this bit. So I have over I have all that over 400 miles per hour, okay? And that, if you crunch the numbers, is like minus 0.1083. Okay, so we have cosine theta is minus 0.1083. All right. If I'm trying to figure out what theta is, what do I do?
Inverse cosine.
Yep, just do cosine inverse of that. And what your calculator is going to report is something like 96.2 degrees. Okay, so that means the angle we're looking for off the x-axis relative to east is 96.2 degrees. But another way we could say this is it's just 6 degrees going this way, right? Because you have 90 and then an additional 6 degrees. So this smaller angle right here is 6 degrees. We could call this 6 degrees. And what should I say next? Using the directions on the map. This is 6 degrees.
West of north.
Yeah, this is west of north because we start at north. And if we go 6 degrees west from there, then we're in the orientation we want to be. So 6 degrees west of north is how you'd want to point the plane in this sort of situation, okay? All right, so the last part, and I think we'll just end it at this last part, is how fast is the plane moving relative to the ground, all right? For that, if we look at our y equation, we might be able to get some insight, okay? So here's what I'm going to do. I'm going to take the exact same original equation that we wrote down, but now I'm just focusing on the y components of it. So I have dpgy equals dpwy plus vwgy. Okay, so for the velocity of the plane relative to the ground, remember it has no x component, it only has a y component. It's a vector that's entirely along the y-axis. So this right here is the full magnitude of that vector. That makes sense? Whenever we have a vector that just lies along one axis, that component is just the magnitude, okay? All right, now we have this, vpwy. Well, if I want the y component, over here we said what the x component was, right? 400 times cosine of the angle. Here, we're going to say 400 miles per hour times sine of the angle, which we found over here. I'm going to write that as 96.2 degrees because we're going to take the angle off the x-axis. That's 96.2 degrees, okay? Then we have the y component of the wind velocity relative to the ground, so that's just going to be 50 times sine of 30. All right, so that's what we have. If you compute this, here's what you'll get. You'll get, if we round to the nearest mile per hour, that's what the problem asks us to do, is 423 miles per hour, okay? So you're getting a bit of an assist from the wind, right? Because the wind, you have a tailwind, but you're also going into it a little bit. So it's not obvious what the answer is, but if you do the math, you see you get a little bit of an assist from the wind, okay? So you'll make it to your destination faster. All right, I think that's going to be it for this part of the review. We're going to just keep going on this stuff on Tuesday. And again, if you want to do test corrections, those will be due on Tuesday. So if you didn't get your test back, come to the front of the room, we'll do it.